Okay, so let's get started. So let's quickly review what we have done, and then we will cover hypothesis testing. Hopefully, we can finish all of them, but if not, then we'll just left some of the material there. But we should be done almost not if not this week, will be next Monday. We should be done for whole thing of this part, and then we left only last two chapters to be finished. Hopefully you can finish everything today. So just quickly review what we have done last time for hypothesis testing. Okay. Seems very weird. Okay. So hypothesis testing is the way, in particular, we focus on population mean. We have some idea where the population mean is, and we try to see if data is supporting that, right? And we learned that from last class there are two types of tests. One is called the Z test, one is called the T test. Z test is when you know the sigma square, the population variance. The T test is you don't know, which is more or less the case, right? So there's two tests. And we also learn if you're proportion, you also do the C test as well, because you don't have to know the population variance, right? By the hypothesis of the population proportion, you know the variance of the sample proportion, because that would be if you hypothesize the population proportion go to A, then will be the variance A times 1 minus A over N. So that would be the done with one sample. And last time we also do the two sample tests, right? And particular, we focus on the case where there's a common variance. Okay? And you have the formula there. And we will learn the other few cases. So before we go, I mean, it's good to review a little bit on the maybe review on this question again to make sure that let's review a little bit about this question quickly to see how to do, right? Because we will be doing some assignment pretty soon. So the question is, I have the population formal normal distribution with standard deviation 4, and with random sample with sample size 64 and sample mean 5, and we want to test hypothesis in two-tailed test is mu equal to 6 and mu not equal to 6, right? But just a gentle reminder, this is what we have, right? Because the sample mean is follow a bell curve, and under the null, this is center at 6, okay? And under this is normal, and this mean of the variance of the sample mean will be sigma square root n, right? Which is 16 over 64, which is 1/4. So the question would be, you want to know, is it going to support the population mean equal to 6 or not? You collect data, you figure out that the sample mean is 5, which is somewhere here, okay? And 5 is less than 6, right? Then you ask whether this 5 is different from 6 enough, right? And remember our H1, the alternative is not equal to 6, right? That means that we allow our type 1 error, right, which is supposed to be true, this may not be rejected and two-sided, right? We ask alpha for 2 here, right? Alpha is being, in general, is 5%. So you want 2.5% on both sides. If 5 is in this purple region, then that is far away enough from 6, then you reject, right? So that is the idea behind the hypothesis testing, right? Assume this is true. We try to see whether it is far away, and then what's the threshold is our type 1 error we propose to satisfy. And how we solve this problem is, of course, we can directly calculate that, right? Because the calculator can do it. But usually we do the standardized because that is checking the same table. So 6 become 0, right? And this 5 become -2. Why? Because the variance of this is 1/4, right? So the standard deviation is 1/2, right? So square sigma over root n is 1/2. So the ST is 1/2. So this is 1 below the mean, so it's -2. Okay. So what you want to do is you can do this area, right? Multiply by 2, that would be the p-value, right? You compare whether it's bigger than alpha or smaller than alpha, right? So this will give you the norm as this, right? -2, true. Okay. And multiply by 2, this gives you the p-value, right? So that would be the idea. You compare this bigger than or less than alpha, this will give you the z-test, okay? Just to remind you, this is z-test. Is there any question before we proceed? I leave you 30 seconds so that you can tell me if you would like to ask any question. Is there a question? If no, then I do the t-test because that will be the same, but instead I replace the sigma by s. Is there any question? No. So the next thing we do is going to review this particular question. Is t-test, okay? Again, I do both tails, okay? The left tail and right tail are similar. So almost the same question. So you have a normal distribution, okay? That means that the sample mean is also normal. Okay? That is done without central limit theorem, but you can always do that. So we have the, we hypothesize this is 4, so this is 4 here. Okay? This again with sigma square over n will be the variance. Okay? And look at the data. Okay. Of course, we will be rejecting if this is it is alpha 2. This is small enough, right? This is because that is determined by our alternative hypothesis. And the question we have is this is 3. The question is 3 is here or 3 is here, right? Is 3 in the orange region or not? Okay. And the problem of this question is if we know the sigma square, then we can do the z-test. And we don't know the sigma square, so we have to do a t-test, right? Because once we place sigma by s, you would convert to t, and t, this will be t15 is n minus 1, and 4 becomes 0, and this 3 become what? It just look at the standard error of the mean will be s over root n. If you don't have you know the sigma, then you use sigma over root n, but you don't know s over n. That would be 2 over 4, right? Which is 1/2. Again, this is -2. Okay. So what you do is look at this area. Okay. And multiply by 2, that will be p-value, right? So it will be t, this -2, 15, true. You multiply by 2 and compare this to the p-value, and this is 0.6, 0.06. That means that is you can't say he's small enough under alpha is 5%. Of course, you use 10% is okay, but use 5% is not. So that's the case where you can't reject H now. Is that okay? Is there any question before I proceed? Because I would like to make sure everyone is all right. Is there a question about that? No? Good. So if no, then I go to the other question. That is the proportion. The proportion we use it the z-test, because proportion have a convenient that once I tell you the mean, I know the variance. Okay. So because of binary data and n is large enough, the sample proportion, which also the sample mean, but now we have CO1, will be a bell curve. And our mean come from the hypothesis is 0.4. But in this particular case, once I know the mean, I know the variance. The variance will be simply 0.4 times 1 minus 0.4 divided by n. Okay, so that would be the variance, right? Because this is the case when you have the binary data, right? Data 0, 1. So that means that when you have data with 0.5, okay, which is here, okay. So the question is 0.5, is it far away from 0.4, right? So we have the rejection region is both alpha over 2 size of the area. So what you do is whether to see the green 0.5, is it in the orange area or not, right? So again, it's normal, and we know the variance is customary to convert to z. 0.4 is 0, and 0.5 is going to be a number that is distant, 0.1, right, over this guy, which is square root of 0.4, 1 minus 0.4 over 50, okay, which is 1.44, right? So what you're going to do is calculate this area, multiply by 2, that would be the p-value. So this area will be norm dot s dot this 1.44 true, okay? But do note that you need this, the right-hand side, 1 minus, okay? And you have to multiply 2 because it's two-sided test. So there's slightly more complicated, okay? You need to 1 minus, because this guy is the left-hand side, 1 minus the right-hand side, you multiply by 2. Okay? So this is the p-value, and you calculate this p-value is fairly large, so that is not sufficient to reject, so you keep x0, okay? Even use 10%, you still can't reject, right? So that is the idea. Is that okay? If there's no further question, then I will continue to review the 2 samples. This is 1 sample. I hope this is good enough for you to remember the things. So if not, then we go to the 2 sample cases. So today, our goal is to finish all of them, so that I think we will release the assignment by the end of maybe by the end of this week, I guess. Yeah, by the end of this week, because the other section have not. We're done by maybe by Wednesday. I guess I will ask the TA to release our assignment. So we finished the first one last class. So I'll review that. Then we'll have 4 more tests to cover. So at least you will see the upcoming 3 will be very similar. The last one will be slightly more different, but the first 3 are the T test, and then with Z test, and the final one with the F test. F test something new compared to what you have learned. But let us go into the T test. Okay, just to remind you, what we're doing is to compare 2 populations. Okay, just a gentle reminder. What we're doing is you have a population 1. Okay, population 1. Okay, itself follow a normal distribution. Okay, some data there. Okay, and the data there we have distribution. We have the mean mu1, and the variance sigma 1 square. Okay. And you have under population. Population 2. Population 1 is here. Okay. And you also have bunch of data. You may have more data in 2. And also this is a bell curve following. Okay, mu2 sigma 2 square. Okay. And the independent, okay, in the sense that if I know everything about 1, I can't say anything about 2. Okay. Even you have everything about 1. So there's nothing you can say about 2. Okay. Or you can have everything about 2, you can't say anything about 1. Okay. So that is the idea, independence. That will help a lot of our calculation. Okay. And these are all the examples. And everything we have one sample case would work as well. What does sample mean? Okay. What is the sample variance? And these are all the sample variances are unbiased estimator. Okay, that's what it said. Okay, and everything for normal. And the first thing will be the idea coming from the property of normal. If your 2 bell curve, the difference of 2 bell is still a bell with the difference in the mean and adding up their variances. Okay. So that's something that we learned from the slide that we talked about we will need now. That is where we need it. So why we want to do compare? Because we want to say is one better than others, right? So if you want to compare 2 store managers, are they who is working better, or 2 stocks, whether one stock has higher return over the others. Okay, this is something that we want to say. Or in the product, is it product A by product B, or channel A by channel B, right? This is very often A/B and A/B testing, right? Compare A and B, how they performs. So this is very common in business application. So that's why you want to know that. So there is a applications that then let's learn how to do it. And there first we learn there's one special case which we often impose to simplify our calculation. It's the case that you assume they have same variance. Okay. And you may ask when we can assume this. At the end, we do the F test. You can test they have different words or not. That we can do. Okay. But at the moment, let's assume it is okay to do it. And we can show you if this is true. Okay. You know that this S1 can be used to estimate sigma. S2 square is also good to estimate sigma, right? Both of them are good estimator. Okay. They're all unbiased. But this is not the most efficient one. Okay. Turn out the most efficient one is the weighted average. This is how we combine them. Okay. They're both, because you can use any number to be any 2 number or 3 number can be used as estimate variance. But sample variance is the lowest variance, the better, more efficient one. So that's why we come up with a better way to combine. And of course, you want to put a higher weight, okay, on the sample that has more sample size, right? So that's why it is a weighted average, right? You put more weights. If N1 is larger, then this SP will be very close to S1. So if N1 is super large compared to N2, right? Then because SP square will be S1 square. If N2 is very big compared to S1, then SP will be close to S2. Okay, so that is, if they're similar in size, then will be in the middle. Okay, so that's a weighted sum. That's why I said the one who has higher sample size will have weighted one. Okay, so this is what we call the pooled variance, and this is one of the most efficient one. Okay, so that's why we use it. So once we know this formula, our life is pretty easy, because if you want to set the same or not, either as x now, then it will be the difference of sample mean will be a bell curve. Center is 0. The 0 comes from your hypothesis. And the variance adding up, right? And now the variance is very simple, because the best guess will be the pooled variance. And the degree of freedom will be n1 plus n2 minus 2. So that would be the way we do. And it's very standard. Also, the interval estimator under the same variance, this is the best guess we'll do, because under the same variance, this is what you do. Okay. If you don't want to assume that, it will be S1 squared, S2 squared. Okay. If you don't allow yourself to say it, but we assume same variance. This is the model we have. Okay. Let us go through the example again, because I guess last time we didn't go slowly enough. So this is the question. Let me write down again. So this is the question. We have sample population 1, okay, which we collect data, which is N1 is 50, X1 is 40, S1 is 4, and the other sample is N2, which is 40, X2 is 42, and S2 is 3. Okay. So this is the question. Okay. And we are doing under the assumption that sigma 1 square equal to sigma 2 square, and that is equal to sigma square. Okay. And our hypothesis testing will be saying that mu1 equal to mu2, and alternative is mu1 not equal to mu2. Okay. So we want to see whether they're the same or not. Okay. If x1 is bigger than or less than the same, but we just where you put alpha over 2 on both sides, or put it one side. So that will be the same thing. Okay. So let us see how we do it. Okay. First thing we know is, because everything a bell, so the difference between these two, sample mean, is also a bell there. This comes from the idea that difference between two bell is also a bell. And under this is 0, right? Because this is mu1 minus mu2. Okay. And what is this variance of this guy, right? The variance of this guy, x1 over x2, right? This will be sigma square over n1 plus sigma square over n2, right? Because it's the first item is the variance of the first bell, x bar 1, and second one is the variance of x2 bar, right? So difference of the variance will be variance of some of them, because independent. Okay. So you look at our exercise, you will see one is 40, one is 42. Okay. So what we have is actually -2 here, right? Because that is. Okay. The question would be, is -2 far away from 0, right? So since we use the two-tailed test, so we want to see where is alpha 2, right? So that would be the question, right? Where's alpha 2 there, right? Or you can look at the p-value. Is this p-value less than 5% or less than alpha, to be more general? Okay. So as we said, how to get sigma, right? We can't get sigma, but that's we use t-test. Okay? So first we calculate this SP square, which is an efficient estimator of sigma, which is N1 minus 1, okay, for S1 square, and N1 minus 1 plus N2 minus 1, N2 minus 1, N1 minus 1 plus N2 minus 1, S2 square. I think this is somewhere like 14 or 12. Let me see. The 12.9. Okay. So this number is 12.9. So the best guess is 12.9. Okay. So be somewhere between 16 and 9. Okay. Because sample variance of 1 is somewhere 9, right? And sample variance of 2 is somewhere, so 1 is for 16 and 2 is for 9. So somewhere between 16 and 9 here. Okay. So we know this estimator, okay? But we know sigma, so we will be using the T. And T, which table to check, will be N1 plus N2 minus 2. So which is T 50 plus 40 minus 2 is 88. Okay. With the active table. And this will be the bell curve. Okay. 0 here. Okay. And what should be 2 here? Negative 2 here. Okay. And we just this divided by square root of this guy, right? The SB. Okay. So this guy will be simply what? Will be this, we call the T statistic, T value will be negative 2 over the square of this guy, SP square over N1, N1 is 50, and SP square over N2 is 40. Okay. And SP is just we figure out. And this answer is negative 2.6. Okay. So the question would be this area times 2, okay? Is it less than 5%? Okay. So what's this area? You have negative 2.625. So with T, this negative 2.625, 88, true. Okay. And remember, you want to find the p-value times 2 because you will be doing 2.625 find area, right? And you compare this to 5%, okay? And that's your answer. I think it's less than 5%, if I remember correctly. So when you look at data, it's like 1%, okay? So that means that it's less than 5%, so you would reject it like 5% or 10%, okay? Not 1%. Almost 1%, but not yet, okay? And that is how we do the test, right? So we say these two samples are different, right? Remember the example why I want to do this, right? Because suppose you are saying, okay, I have one store, have mean this, variant this. I have another store, mean this, variant this. You want to see these two stores are different or not, right? Or there's 2 managers there, or 2 products there, or 2 vaccine there, right? There's A/B is very commonly you compare 2 performance of 2 staff, okay? And finally, I would said already in the last class as well is, if you don't want to do hypothesis testing, you want to predict the difference, right? So you would do interval estimator, right? This negative 2 is a point estimate, right? If you just compare You make an estimate by point. -2 is a point estimate. But if you want to do an interval estimator, you add the critical value, right, and multiply by the variance, the standard deviation, right? So this is the critical value, right, come from here, right? Remember, critical value is simply that TA, right? 0 here. You put 2.5 says 2.5% each, right? And Excel formula will be this T inverse 0.025 ATA, okay? And for this guy will be T inverse 0.975 ATA, okay? So this will be the two critical value, but one with plus, one with minus, so that's why plus minus, okay? And multiply by the standard deviation, right? We know that already well. Is that okay? So this is a long review. Why I do that? Because you will see immediately that will be very similar to this. Okay. The only trouble is how to calculate how to calculate this FDA. Okay. Inside is much easier, but the table to check will be more difficult. Is that a question? So let me tell you this one. Okay. When we have unequal variance, okay, and then we can't really simplify the variance, right? So because they're different, S1 is a good estimator for sigma 1, and S2 squared is a good estimator as S2 squared. So that's why you can't simplify. That's what you get. Okay. And you imagine I got the same formula here. Okay. And okay, this is easier. But the difficult part is the V, what's the V? Okay. Which table of T to check? That become very complicated, turn out to be. And this V is coming from a most crazy formula in this class. I hope you are ready. Will be this. Okay. Of course. Luckily, you have infinite cheat sheet you can bring, so that's why there's not an issue. But this we come with this one, and you ask, okay, what's this? But I can't answer that. That's based on some math formula. Okay, math derivation. I'm not even showing it in our class because the proof will be very complicated to do it. Probably you have to go to graduate school to understand. Not even graduate school. I think you have to go to STAT master to learn it. I mean, no master in B school actually teach this. Okay, I have to go to the STAT department to understand what's going on. So just take it. Okay, I don't understand what's going on, but let's see how to operate it. Okay, so you will be the same thing here and the same thing here. There's nothing deep inside. Okay. So you see, I use the same question, same number here, but now I don't have the assumption that they're similar. Okay. So let's see how this question is being done. Okay. So I have the same question here, but now I no longer have this one. Okay. So that's different is this one no longer valid. Okay. So let me write that again. Okay. Let me write that again. The question we have is the following. So with two population, N1 is 50, X1 bar is 40, S1 is 4, N2 is 40, X bar 2 is 42, and S2 is 3. Okay, so remember we no longer have this. Okay, no longer they're not the same. Okay, so how to guess this guy? You have to have used S1 square. How to guess this guy? you have to use S2 squared. So there's no shortcut to it. Before we know they're the same, there's some way to combine the two things to get a better estimator. But now they're different. We can't really do anything because they're not the same. So we can't simplify. Okay. So remember our null hypothesis is mu1 equal to mu2. And they're not the same. So if you look at this carefully, this is still a bell curve. I guess that's not a problem. For observation x1 bar minus x2 bar, right? It's still a bell curve there. Okay. And it's still center at 0. There's no difference from before, right? Because this is under our null hypothesis, right? And the variance of this is still now different, will be sigma 1 square n1 plus sigma 2 square over n2. Okay, they no longer equal to sigma, right? Because before we assume the same, then the formula is easier, but now we don't. Okay, so now the question would be, because we have this guy, right? This guy, right? So that means that we will reject on the both sides, which is too far away from 0. So that's will be our rejection region. That is our type 1 error we want to commit, right? Even though it's true, we can end up in these two extreme values. So we have to decide what is the area that say far away now. And the data we got is 40 and 2, so it's -2 again. So the question is -2 is here or actually here. So it's this or this. If in the purple area, then reject. If not purple area, then we don't reject. Okay, so I think very similar as we have said. Okay, so now what we're going to do is, if we know sigma 1, sigma 2, then it's very simple. It's a bell curve, then we're done. Okay, but the problem is not, we don't know this two guy, so we have to rely on something called T, right? But this T is rather complicated. It's based on the derivative V, which V will be coming from a super complicated formula, which we will visit soon. But this is 0 again, okay? And what is this -2 here, okay? This T value, right, we call test statistics, will be -2 over square root of this guy, because this is standard deviation, the square root of this guy. Because we replace sigma 1 by S1 square, right? This is why we have T, right? So this is 0 by N1 plus S2 square over N2, right? S1 is here, S1 is here, N1 is here, right? So I think it's -2.7. If I remember correctly, let me see. Yeah, -2.7. Okay. And before we are going to calculate this area, on the left-hand side times 2 to get the p-value, we need to know what's the V, right? If we don't know the V, then we don't know which table to check. Okay? The V function will be super crazy, which I'm not going to copy because it's like this one. Okay? It's like something you would calculate if you don't have nothing to do in your free time, right? So, and this V turn out to be, you would take, once you calculate that, you would take the integer part, right? So you run down, okay? And look at the slides. And this V is 87, okay? So compare to the previous case, which is 88, okay? And now 87. So you will say, oh, not much difference, so why bother, okay? For this particular case, this is very similar. But in general, can be very different, okay? Can be something like one can be 100 and one can be 50. It can be like this. Depends on how the S1, S2 are different. So, but in this particular case, they're so similar. Okay, but that's okay. But at least we can do the calculation. Okay, calculate this area times 2 with p-value. So the p-value will be t this negative 2.7 87 true. Okay, and times 2. Okay, this with the p-value. And once at the p-value, I compare it to alpha, right? Whether it's more than 5% or less than 5%, right? If I ask you use 5% as a type of error. So the p-value turned out to be 0.8%. Okay. So you will, of course, reject 5%, 1%, 10%, and any percent you use, right? 1%, 5 or 10, you all reject. Right? So it's far away now. Right? So the p-value, you will see the same question is indeed compared to the previous one, is indeed smaller. Right? In this particular case, turn out to be smaller. Okay. And similarly, you can do the interval estimation, right? If you guess the difference, -2 will be a point estimate. Okay? And this will be your interval estimate, right? How do you get that, right? This is the standard deviation, right? There will be the denominator of the t statistics, okay? And this is the critical value. You remember, right? This is T88, sorry, 87 in this case now. T87, okay? There's a bell curve here, right? It's a 0. And you want 0.025. This is 0.025, right? So this number will be T inverse 0.025, 87. And this number will be T inverse 0.975, 87. One will be 1.97, 1.987. The other will be negative 1.987. So this, just plug in this number, and then we're done. Is that a question? Okay. So you done of the two tests, you done the 2 sample tests. So this is what we call A/B testing. Okay. And that's very common use in business. Okay. And after the break, we'll teach you a more advanced version of A/B test, which is available if the same subject receive different treatment called pair population. So just a remind, we can do it after the break. Will be something like this. It's like the following. We have population 1, okay, population 2, okay, and we said before these population are independent, right? But now, suppose they're not independent. Suppose indeed this guy number 1, you can identify them here, okay? And they're the same guy number 1, okay? And you have woman number 2 here, and the same woman, okay? And why don't do that? Because guy number 1 is may have used product A, population 1, and product B, right? And you want to see whether he is using, say, like A more than B, right? Or using time, right? You have internet interface, right? One use A interface, you also use the new interface, and you want to see the difference. Okay, you have the same individual, we subject to different treatment or different product. Okay, and you want to see different product how they do, right? Or very often, 1 and 2 may be before and after, right? Maybe 1 is before they take the medicine, and B they after, right? Or maybe 1 he do not have vaccine, and after they have vaccine, right? So you compare treatment across different thing, and you have keep the same individual, and you want to look at the difference between them. Okay, so this is a special case of A/B testing. Compare two scenario, but you're able to look at the same guy, same individual across different situations. Okay, and you want to, because of you control the same guy, the difference between these two situations will be the result of difference between. Okay, so I will talk about this after break. So, and I guess as usual, we'll be doing the U reply. So I'll see you in 15 minutes. Let's meet at 15 minutes later. So let us continue. Okay. So, hi, windy day. So, someone said your hope is to go to school. That's good. I hope that is the truth. The answer is yes. It's a mandatory day off, which I can't really control. So that would have to be day off. And for makeup, as I said, at the end of the semester, let's see how many makeup we will do. We will make up on the makeup days for optional Python or R tutorial. So that is upper exam. So it's completely optional. I will just book the computer lab and see if you come, and then we talk about some Python. Okay, it's completely optional because it's already after our exam is over. So exam is November. We will do in December. So you don't come, you just look at the record, okay, or we talk about that. Because we only do Excel in this class, so Python would be pretty useful. Probably we'll do some makeup, of course. We'll see if that will be done. Yeah. Oh, already someone in the first day, but in the first day you don't have the class. So, but anyway, just make sure that you know there's no class on first day. It's very windy. I guess that's true. But it's getting more windy in this November. For those who are not from Hong Kong, you know, November will be windy season. I mean, probably your second year, probably you already know this. November will be a windy season. Yeah, t-test, complicated V. Yeah, that's true. Well, there's something we learn. And unequal variance. Yeah. And t-test both tell. One tell the same, right? One tell we just do the p-value and then calculate accordingly. Right? That's not something that super complicated to see how it works. Yeah, two sample. I guess you know very well. The speed so far is good. I guess you can see it's not too deep, too difficult. Most of you are okay, so I'm very happy. Oh, very happily, we have some free happy person here. Okay, we have someone who is not so tired. I hope so. After the Halloween, I guess we gain some energy, having more candy, hopefully. But it's important because this month is our last month. So final lab. So after this, and we have enjoy our holiday. And luckily, we don't have central exam. So we end November. When we're done, right? So nothing in the December for us, right? November is over. Okay. Sorry. T-test. Can you share one fact about yourself? I'm not sure what is fun fact, but I do enjoy cooking. So I do. I think I do pretty good fried rice and fried noodle. And that is not easy. If you ask a Cantonese cook, one of the things to check is how to cook fried rice. I think I do pretty good fried rice, which is something my kid likes, my fried rice and also fried noodle. I don't know whether it's fun or not, but that's what I do. Healthy jokes, yeah. Yeah, but I don't know whether it's fun or not, but now I no longer being more fun because actually my wife talks about me because before she knows me, I'm a Ph.D. student, I'm pretty much more fun, more humorous. But after I get into more research, I become so deep inside the research, I lose the humor. Looks like a different person. So I no longer become more telling more jokes than I used to tell. But that is how life changed a person. So probably when it get to the real world, probably you lose the the fun part of yourself. But hopefully still keep your character for a little bit. So let's continue. We mentioned the paired population, right? It's in these two populations, you can connect them. So it is exactly opposite case of independent, right? So it's completely related, right? And very often is we would call treatment, okay? With this individual, is before treatment, after treatment. And we want to say if the treatment would matter, right? So this is the best scenario if you want to do A/B testing, right? So if the same person who use your system, how he like your product, and he usually exposed to your new product, and you want to see two different products, how they react, right? So that is something that you want to see the effect, right? So we'll define treatment effect is the difference between before and after. So just look at this, okay? This will be X11, okay? Maybe use other color to avoid confusion. So this is X11 and this X21, okay? And this is X12 and this is X22. So the difference between that, right, is called D1. The difference between that is called D2. D1 can be represented by, say, will be X11 minus X21. D2 will be X12 minus X22, right? So it's left minus right, okay? So that is the difference. And if we assume the difference follow the bell curve, right? We assume this is follow the bell curve, and it will mean 0, right? And the variance will be sigma square over n, right? And this is simply what? One sample test, right? Just difference is a bell curve. So a bell curve means 0. You want to test it, right? It's just simple one sample test, right? You will be rejecting if our norm office is like this, right? X0 is D is equal to 0, right? D not equal to 0, X1. You want to say, I'll put you here. So if you don't know sigma, you use the S, then there will be the t-test, right? Standard t-test. Okay, so that will be the idea behind it. Okay, so let us see the slides again. That will be the idea, right? So just like you calculate the mean, you calculate SD, right? The standard thing, right? And once you calculate that, you do the standard t-test, that we're done, right? So there's nothing new. This one, this is just simply a t-test, and this is simply the way you calculate the interval estimator, right? So there's nothing very deep here. So let us actually work on this problem. Is you have data about the treatment group and control group, okay? And you have sample size of 16, all right? And difference is 1, and SD is 2, and then how calculate, right? So remember, this is a bell curve, right? So this guy, it's the color, right? The D will follow a bell curve, right? And will be centered at 0. This is sigma square over root n. Okay. And we said this is different from 0. All right. If we put alpha over 2 here. Okay. So if this is far away from 0, the difference, right? Then we say the difference, right? Okay. Of course, remember you can also do one-side test. It depends on what your alternative is, right? But we always do two sides for the convenience. But you can always do one side, right? If you do one side, put alpha on one end, put all the alpha on one side, right? Two-sided, you separate alpha on both. Okay. And you figure out that the data, the average of difference is 1, right? So it's somewhere here, it's 1. Okay. It's here or it can be here. I don't know. It's here or here. The question, I don't know. If the line is in the orange area, then you reject. If not, then you don't, right? And if you know the sigma square, then we are done, but we don't know, unfortunately. Right? So what we're going to do is to use the t, right? And t is n minus 1, so t15. And this will be, the 0 will be 0. And 1 is what? The t statistics is this 1 minus 0, right? How far away from the mean? And over the ST is 2 over root n. Okay, n is 16. So this is actually, again, is 4 over 16 is 1/4. So this 1/2. So this is 2, right? Because it's 1 over 1/2, which is 2. Okay. So we do the two-tailed test. That means that this area and this area I multiply by 2 and compare to alpha, which is 5%. Right? How can we calculate this area? I think you know very well, but I just bore you to the death. Just t this 2 15 true. But you remember it should be 1 minus. The reason is you only have the error on the left-hand side because f is on the left-hand side, right? Then because two-tailed test, you multiply by 2. Okay. So this turnout is like 6%. Okay. 6.3%. So that means that if you use 5%, you can't reject. 10% you can reject. 1% you can't. Okay. So since we do 5%, then we can't reject, right? We'll keep the action out. Okay. Is that okay? Of course, in case you really want to use critical value, right? You'll be doing this T15, right? 0 here. You want to calculate this 0.025, this area 0.025. If you use 5%, and this number will be T inverse 0.025, 15, and this number will be T inverse 0.975, 15, right? Both they will give you 2.13145 plus minus for either of them, and 2 is not there, right? Because 2 will be somewhere here, okay? So it's not in the rejection region, so you can't reject. Is that okay? Sorry. I guess I should be coughing this week, but next week I should be fine. You'll see on Monday and we should be fine. Is that okay? Any question before we proceed? Okay. So basically we've done the two A/B testing, right? So either you have the same variance or different variance of independent sample, or you have some observation you observe before and after, right? The same individual is the same. Okay. So there's two extreme cases, right? Of course, there are many intermediate cases, but in our class, we focus on two extreme cases. One case is whether they're completely independent, right? Completely independent, you have two cases. You have same variance or different variance. Or you're completely connected. You can say, you can observe the same individual in two different settings. You want to see the different treatment effect, right? So this is very common in a lot of A/B testing. Okay? Any question? Any question? Okay. If no, okay. Is there any question? No. Then we go to something is not difficult. We'll do different proportion. Okay. Also, something we care a lot. We're binary data. Is that okay? So, so here, remember proportion. When n is large enough, you follow normal bell, and difference in bell is also a bell, right? You just subtract their mean is a new mean, add up their variance as a new variance, as long as two proportion independent, right? So you can always apply that. So why you want to know this, right? Because suppose you want to know how many people like your product or buy your product. You want to compare across different products, or how the popularity of difference, or how many people like your product across two different cities, right? Across the different product type. Okay? That was something we do often, right? Compare two different cases, right? Or P1 may be proportional of people who like stat class, right? And you want to compare across, say, those who are accounting major, or compare those who are non-accounting major, right? Maybe accounting people like to work with number, and they like more stat or not, right? Depends on like this, or this kind of question you want to ask. So one of the interesting thing is, if you assume they have the same mean, which is same proportion, then we can come up with a better estimate of the overall mean, right? Because the same thing, right? Then combine them, that give you a better mean, right? Because, let me say it. To estimate pi1, you can use P1. Okay. If you have pi2, you can also P2. Okay. Of course, P1 and P2 are valid estimator for pi, right? But they are not the most efficient one. As actually any combination, any weighted average would work for P1 and P2. Say use half of P1, half of P2 would also work for pi. Or 1/3 of P1 and 2/3 of P2 were a good estimate of pi. Okay? But turn out that you can show this is the best for the pi. Okay? And this is very natural, because when you say pi1 equal to pi2, that means that the same thing, right? So you can just add up how many thing in 1, how many in 2, and how many of them say yes, it's x1, x2, then you're done, right? Because the same thing. You don't distinguish of them, right? So they're actually the same population, right? You can combine them, right? If you say the city 1 and city 2 have the same proportion, so you don't really want to distinguish them, right? You just calculate how many of people say yes and how many people in these two cities, and they're done, right? Because there's no difference between them, right? Because proportion data, the difference is number of people who say yes, right? So you can do this. It's called the P bar. Okay, this is the better estimate. Yeah, I think I proved that somewhere. I didn't prove it, or I prove it somewhere here. That's the most efficient one, what is called a smaller variance. Actually, I have the proof, but I guess you don't care. Okay. So this is the set test statistics. Is the same thing here, but remember, we can use a better estimator for our P. That means that we have the equal variance approach, right? So the difference you can see, when you compare proportion, we can use the equal variance idea, okay? Because this is our P bar times what's that? It's actually sigma or SP squared. It's SP squared. The pooled variance idea. Okay. So this is the formula, and everyone the same. Okay. But be careful. Okay. The tricky thing is when you have interval estimator. Okay. We can't use P bar here. Okay. Or classically, they don't use P bar here. They still use separate them. Okay. The reason is unless you assume pi 1 equal to pi 2, right? But if you assume that actually no need to do interval estimator, right? If they're the same, they should be 0. So that's why we will keep this instead of using pi bar. Okay. That is something a little bit tricky here. Okay. But otherwise, this is the only tricky part. Okay. Compared to the thing in the O. Okay. So let us see this example here. Okay. Once you know that, it should be obvious. So we have a two set of data of binary is yes, no question, yes, no data. And we have 50 people from one population with a sample proportion 0.6. Okay. So it means that actually 30 people say yes, right? And 20 people say no, right? And the other population with 40 people and 0.7 people say yes, so it's 28 people say yes, 12 people say no, right? So that would be actually the data you got, right? So now the question would be, okay, are they the same proportion in population or not? Okay. So to repeat, if you look at P1 minus P2, it will be a bell curve, right? And mean 0. Okay. And we know under this now, what should be the variance? The variance, of course, will be pi 1 minus pi 1 over n1 plus pi 2 1 minus pi 2 over n2, right? But now we know that pi 1 and pi 2 equal to pi, the same, right? And the best guess will be coming from forgetting about the difference, our P bar, which estimating pi, will be just adding how many sample we have with 50 times 40. Okay, how many say yes? 30 plus 28. Right, because so that's why 58 over 90. Right, so you forget about the two population here. You combine how many yes over how many people. That will be best guess because that's the most efficient estimator here. Okay, so 58 is the most efficient estimator for the pi. So just put this number back to here because they're all pi. Okay, and you know that the proportion for one is 0.6, one is 0.7. So the difference is negative 0.1. Okay. Again, as you would say, you would put the alpha over to here, alpha over to there. Okay. The question is 0.1 in the purple region or not, right? Or you can calculate the critical value, then we're done. Is that okay? Is the whole logic, right? It's not something too crazy, okay? Because we're using all the same logic again, again, and again. Right? It's embarrassingly boring, but we have to do that. Okay? So if you look at the calculation, right, and which is on the next slide, okay, which you can calculate because this P you can always convert to Z, means 0. Okay, and what's 0.1 here? So you'll be negative 0.1 minus 0, the distance, over the square of this guy, right? Which will be this P bar, 1 minus P bar, right? And 1 over 50 plus 1 over 40, right? Or I can just do the calculation. Turn out to be negative 0.9. Okay, negative 0.9. So the question is this area, okay, and this P value will be norm dot S dot this, okay, 0.09 true, okay, and multiplied by 2, okay, and of course you can easily see that upon 9 will be not enough, right, for 5%, right? It's somewhere between 1.9, right? So it's not, you definitely cannot reject this one, right? Because this is somewhat the P value going to be 3%, right? So this value is going to be like multiplied by 2 is going to be 3%, 0.3, right? 30%. So no matter use 10%, 5%, 1%, we can't keep it. Is that okay? Is there any question that I can help? Is it okay? Okay. And let me erase this one. Okay. So you can also do the interval estimator. So this is to be -1, will be a point estimate. And confidence level will be like this, right? This is the critical value. And do note that when we have interval estimate, We do not assume they're the same, because once they're the same, then we're done, right? So we don't make the assumption that they're the same variance. So that's why we use the one separately. So that is we don't have the same pool variance assumption. Okay, so this is the part that need to be a little bit more careful. But otherwise, everything is very straightforward. Okay. Is that okay? Because if we assume P bar here, then we are done. Actually, we don't have anything to say. Okay. Is that okay? So if there's no more question, then we will come to the very last test. Okay. And once you learn that, basically we learn all the basic thing from this class. The last two topic will be application. Okay. We'll be applying what we call general linear model, which include two things, ANOVA and regression. Okay. So this is the very last thing that is a theory. After that, we'll do application. Okay. So the very last is called the F test. And as you can see, this is the first time we depart from population mean. We talk about population variance. And we want to look at whether population variance are same or not. Okay. And why we want to look at this is, remember, variance is one of the measures, is the risk in security, right? You want to look at the risk of the stock. Okay. And variance is one way to look at it, right? So we want to check if the same variance or not, right? And also remember, when we do two sample t-tests, we want to say the same variance or different variance. How can you do that? This test will tell us whether you have that. Okay? Compare the variance. And if you remember, if there are two bell, okay, two bell curve, x1 bar, x2 bar, right? And this, I don't know, mu1 is mu2, right? The variance mu1 square over n1 and mu2 square n2, right? Okay. Or actually, we don't have to, the bar doesn't matter anyway. So this, or two population here, okay? And we want to check if their variance the same, okay? And we just simply take the ratio of the sample variance, okay? We want to see this two bell curve have same variance or not. Just take the ratio of their variance, okay? The sample variance. And turn out that when you compare them, you just look at the F table. And F table is very complicated. You have to not look at one number. You have two numbers. It depends on the sample size of the numerator and denominator. T table only have one thing to check, but F table, you have to check two numbers. Okay, give me two numbers, I give you one table. Okay. And remember, this F is always positive, and the F would also often look like this style. Okay. And again, this is a two-tail test here. Okay. So you would reject if alpha of 2 on this side, alpha of 2 on that side. So it's a two-tail test here. If you don't know which one is larger, it's two-tail test. Okay. And in the later application, you will see we often do one-tail test. Okay. But in this particular case, we do two-tail. Okay. In later application, we often see we do one-tail test because we know which should be larger. But here, it's a two-tail test. Okay. So this is a two bell curve. I want to compare their variance. want to check if they have same variance or different variance or one bigger than others, you can use this approach. Okay. So let me show you the application. Okay. So we have a two bell curve. Okay. First bell curve, the variance 30, have sample size 50, and the other has sample size 40, variance 20. So the question give you is N1 is 50, S1 square is 30. Okay? And the other one will be N2 is 40, and S2 square is 20. Okay. So the question is how can you test this? Okay. And it's very simple. The F statistic is just S1 square over S2 square. Rather simple. So we just take the difference between these two. Say 30 over 20, which is 1.5. And it will look like this, the F. The F look like this. Something like this, I guess. Okay. And of course, remember, you will try to put alpha over to here and alpha to here. Okay. And 0 is somewhere here, right? Because the F cannot go below 0. Okay. And which F table we're going to check? Numerator is N1 minus 1, so it's look at 49. Okay. And what's N2 here? Is 39. So if 1.5 is in either this area, you reject. Okay. So let's look at these two numbers first before we talk about p-value. And this value will be F inverse 0.025, 49, 49. Okay. And this one will be F 0.975, 49, 49. Okay. So, and this turned out to be, as you see, 0.55, and this is 1.8. So that means that 1.5 is somewhere here. Okay. So since 1.5 is not in this two rejection region, so we don't reject. So this critical value method is pretty convenient. Okay. But now, if you want to use p-value method, that is a little bit complicated. Okay. Because this is not symmetric, the F is like a weird shape. So the p-value method involves the following. Okay. You need to calculate this area to the left or to the right. Okay. Pick the smaller side, multiply by 2. Why? Because that will be you adjust the alpha, right? So you adjust the alpha, such smallest alpha such that you reject, right? So just the first one you see, multiply by 2. So that's why you pick the one that is smaller, multiply by 2, right? Because you pick the larger one, multiply by 2 is more than 1, right? Because this is left and right, right? One side must be less than 0.5, the other side must be more than 0.5. So you pick the one less than 0.5, multiply by 2. Okay. So in this case, you will do F dot inverse, okay? Sorry, will be F this 1.5, okay? 49, 39, true, okay? And check this number is more than 0.5 or less than 0.5. If less than 0.5, multiply by 2. More than 0.5, 1 minus this and times 2. Okay? So that's why if you do Excel, will be minimum of this and 1 minus this times 2. So the Excel formula is slightly more complicated. Okay? So if you really want the formula, will be 2 times minimum F this 1.5, 49, 39, true, comma, 1 minus F dot this 1.5, 39, 49, true, close bracket. So you take the minimum of the two number, multiply by 2, okay? Because you can't take the one that more than 0.5, right? You multiply by 2, then it's explode more than 1, right? So you take the smaller one, because remember that y is true because you keep moving the alpha such that you just reject, right? So that means that you have the minimum of the two number. Okay? So we're done. So you know the F test, know everything. So you can enjoy the graduation ceremony if you have a senior cohort that you have to go to there, but otherwise I will see you on next Monday. So I would ask the TA to release the homework this week so that you can have time to have fun before the weekend. Okay, I'll see you on Monday.